There we go. Alrighty, so we last left off, we started talking about entropy, and we had covered some sample problems looking at entropy, oops, the next previous page, and talked about how entropy was related to the reverse of the heat of a system, from a disorganization perspective, right? If you heat something up, it becomes more disorganized, so it kind of makes sense. We had just started talking about the second law, which basically states the entropy of the universe increases in any spontaneous process. And we talked briefly about the reversible and irreversible processes. We're just about to get started on this slide right here. And with this slide, we're going to talk more kind of microscopic, right? The previous slide is, talking about universe. This slide, we're going to talk microscopic and think about what it means on a molecular scale in terms of entropy. So if we have, in this example, we have two molecules, right? These two molecules, they're colored, one's red and one's blue, so you can keep track of them, and they're sealed in the left-hand side of the container. If we then take the valve and we just simply open the valve, right? We open up the valve, then both of these molecules have the ability to move, right? We can have the blue on the left and the red on the right, the red on the left, the blue on the right. We could have both of them on the left and both of them on the right. Okay, so there's four possible, what we'll call microstates, once you open up the stopcock valve. So you have the ability to have four possibilities, right? At any one point in time, if we assume the balls obviously aren't, we're not including sitting in the tube in between, they're going to be in one of these four possible positions. So when we thinking about that, this is a scientist, his name was Boltzmann. So the Boltzmann basically studied this to try to have a better understanding of what was going on. So, when we're talking in particular about gas, so right now we're talking about gas molecule expansion. So when two molecules start on one side, like above, what's the likelihood they end up back on that exact same side? So what's the likelihood that if they start here on the left, that they end up in this particular left-hand side, right? So we have two possible balls, right? So the two balls, and somebody's microphone got unmuted. No, what happened? How strange. Some background noise just came in. So there's two possible balls, and there are four possible microstates that exist. So there's the likelihood, we're talking about probability. Probability has to do with the number of items that there exist divided by the number of positions they could be in squared. So 2/4 is the same thing as half, right? 1/2 squared is equal to 1/4, right? 1/2 squared is equal to 1/4, which means if we think about this, right, this is 0.25 is a probability, which is basically equal to a 25% probability that we will end up with having both of the balls on the left-hand side as shown in the original picture A. So we're talking about probability, there's a mathematical formula, right? It's the number of molecules divided by the number of positions that exist. There are four positions, right? And we square that. And you can see it equals 25%. 25% likelihood. Now, if instead of looking at two molecules, let's just say we use 1 mole, right? 1 mole is Avogadro's number, right? I'm sorry, I explained this incorrectly. This is the 2 here is the two possible positions, right? This is positions, right? This is possibilities. down below, and this is the number of molecules. Right, so we have two possible positions, the left and the right. That was my bad. The left and the right position. And that gives us a total of 4 possibilities, as we see on the right-hand side. And there are 2 molecules, so we end up with a 25% chance that we end up with all the balls in the original position. If we use 1 mole, right, if we use 1 mole instead, right, this is going to be the same 1/2 to, instead of 2, we're going to be using, Avogadro's number. So instead of 2, we have Avogadro's number here. And if you take 1/2 to the 6.02 times 10 to the 23rd power, this number equals 0, right? Essentially 0. It's a 0 chance that they're going to be where they started. It's infinitesimally small, basically, which makes sense, right? If you take a half and multiply it by a half, it's, a quarter. You take a quarter, multiply that by another half again, right? Then you're at an 1/8. Then you're at a 16th, then a 32nd, 64th, and you keep working your way down, 6.02 times 10 to the 23rd times, and you're going to be infinitesimally small. So when we're talking about, being able to identify where molecules are, it's going to be extremely difficult, right? So we continue. So gases spontaneously expand to fill a given volume. So the most probable arrangement is approximately equal, with approximately equal molecules on each side. So the same thing. We started a gas at 1 atmosphere with 0 atmosphere or vacuum on the other side. If we then open up the stopcock, what's going to happen, right? You open the stopcock and you have a spontaneous expansion event occurs, moving more or less half of the atmosphere's pressure of gas to the left-hand side and half to the right-hand side. Right. So since the forward process is spontaneous, obviously the reverse process is not spontaneous, right? There's no way to get all of the gas to return back into the initial chamber A, right? With this valve being open. Right, makes sense. It's common sense stuff we're talking about here. All right, statistical thermodynamics. So thermodynamics looks at the bulk properties of substances, or essentially the big picture. We have seen what happens on the molecular scale, and how does that relate to the big picture or the thermodynamic scale? So we use statistics or probability to relate them. The field is called statistical thermodynamics. And when we're talking about statistical thermodynamics, we're going to be looking at individual states. We're going to call these microstates, which is a single possible arrangement of position and kinetic energy of the molecules. So when we're talking about, when we're doing these types of calculations, we're taking snapshots. We're going to call these microstates, and we're looking at what's going on at that particular moment. Where are all the molecules arranged? What is the energy of the molecules at that instant in time? And this refers back to the scientist Boltzmann, right? And Boltzmann used these microstates. So because there are so many possible microstates, we can't look at every single picture, right? So you have infinite number of microstates. So what you end up doing is we're going to use this letter W, and that's going to represent the total possible number of microstates, right? And when we look at entropy, entropy is a measure of how many microstates are associated with a particular macroscopic state. We'll go through the math in a second, and it'll hopefully make a little bit more sense. So the connection between the number of microstates and the entropy of the system is listed here, right? Where we have entropy of the system is equal to some constant. In this case, it's the Boltzmann constant times the natural log of the number of microstates. Right. So what we're doing here is, if you are thinking about it from a mathematical perspective, right, you have your you take the natural log. If you have 2 microstates, right, you have 0.693 is the natural log times the Boltzmann constant. If we have 4, natural log of 4 is 1.38. So you have this proportional increase that occurs as you increase the number of microstates. So as W increase, you see this proportional increase in the total number of microstates, proportional increase on the right-hand side, and it's related to this Boltzmann constant, right? So, and the Boltzmann constant, it's a tiny number. So more microstates you have, the larger the entropy is, the more disorder that exists, which makes sense. Let's just say you have a container, right? A sealed container, you have two molecules in it, right? And if you compare that to a container with, I don't know, 9 molecules in it or 10 molecules, right? You have many more possible states with 9 molecules versus 2. And I think that we're going to cover that in a slide or two as well. So you think about that. You have a lot more possible microstates, a lot more possible disorder that exists when you have, more molecules. So entropy is going to increase. And since entropy is a state function, the final value minus the initial value will give the overall change, right? So when we're thinking of entropy again, right, it's a state function. What is the state that it's in at one point versus the state that it's in another point? We don't care how it gets there, right? If we, we have, this container again, going from the initial, right, our initial and our final, right? We don't care that this moved all the way around like so to get there, and this one only moved here. We don't care about the path. It's not a path function. All we care about is what does it look like at the beginning and the end. That's all the state function means. So in this case, an increase in the number of microstates results in a positive entropy change or more disorder, right? So when we think about a final minus initial, natural progression is to end up with more disorder versus your initial state. And that gives you this equation right here, right? So the change in entropy is related to the, related to this equation here, right? The entropy equation, the final minus the initial, right? And that's what you get for the overall entropy change. And if you look, you can rearrange, since you have natural log in the equation, we can rearrange the equation to end up with natural log of final over the initial times the Boltzmann constant gives us our overall entropy. All right. So, this is just kind of giving us a big picture of what's going on for entropy. This isn't something that's typically measured on a regular basis, right? We can't usually measure the number of microstates in any particular fashion. So we have to think about it in terms of volume and temperature changes on the system, right? We're not able to take a picture and measure the energy of each individual molecule and where they each stand in space, both before and after. But we can do that through other terms, right? We can look at the volume of a system. We can measure the temperature of a system and get overall averages. So if we increase the volume, there are more positions possible for the molecules. This results in more microstates, so increased entropy, right? So if you have, again, a container here and a container here, right? There's many more positions available on the right-hand side because it's a larger volume, right? Increased volume, you have increased entropy, increased possible number of positions. Same thing, if we increase the temperature, right, the average kinetic energy increases. This results in a greater distribution of molecular speeds. Therefore, there are more possible kinetic energy values, resulting in more microstates, which are increasing entropy. Again, we have the same thing, right? Initially you have cold molecules. They're each moving very slowly, different directions. If you warm the system up, right? Oops. Warm the system up. One molecule is moving very quickly. The other one just a little bit more quickly. right? But you have that increased temperature allows them to move to many more different locations over time. And that increased temperature is therefore going to increase entropy. So molecular motions. So in addition to molecules simply moving about within a container, there are other types of motions that exist, right? The first one is the one that we just talked about. It's translational motion. Right? A molecule can just move as an entire molecule from one place to another. That's the easiest thing to picture in your mind. But there are other types of motions that a molecule makes, right? There are vibrational motions. Vibrational motion is a periodic motion of atoms within a molecule, right? We have pictures of them down below, right? If you think about each of these bonds, when this bond is, when they're both expanding at the same exact time, right, on either side, the bonds are just stretching, right? You could have the bonds vibrating back and forth. You could have one expanding while the other one is contracting, right? So you have vibrational motions that exist within molecules. You also have rotational motions, right? The molecule could be sitting in space and just simply rotating. Right? That's just a picture of what's going on here, right? You have a rotation that occurs, and these are all motions that exist. Each of these create separate microstates, right? You can imagine that a molecule that's rotating when it's in, vibrating at the exact same time is going to be different than a molecule that's simply rotating. Different number of microstates, different positions of each of the individual atoms. And this is directly related, obviously, to the number of atoms that exist. The more atoms means more microstates, means more possible molecular motions, right? So right here, we just looked at water. This is a picture of water down below. We have 3 different vibrational motions that exist, 1 rotational motion. We could probably think of other rotational motions, right? So there's lots of different possible motions. Imagine if we just simply start connecting and have, more and more atoms attached, right? More and more atoms attached, you have a lot more different, movements that can occur all at the exact same time. So if we think about entropy on the molecular scale, so the number of microstates and therefore the entropy tend to increase with increases in temperature, increases in volume, and increases in the number of independently moving molecules, right? So you can see entropy is directly affected by these 3 things here. We think about in comparison to physical states, if entropy increases with the freedom of motion of molecules, right? So if you have the entropy of a particular molecule in the gas state is going to be much larger than the entropy in its liquid state than its solid state, right? And it makes sense, right? A gas molecule, you can just look at the dust particles floating in the room. If you have any sun floating in through your window, you can see, and imagine those are individual gas molecules. You could see lots of movement occurring. It can travel across the entire room, create lots of different microstates. Liquid, it's going to be confined to a cup, for example, whereas the solid, the individual molecules are stuck in their individual positions, but they can vibrate. Some of them may even be able to rotate. They have the different vibrations that are available to them. But a lot less overall movement. So the entropy of the system increases for processes where gases form from either solids or liquids, right? So if you're going directly from a liquid state to a solid state, you're going to see, a liquid state to a gas state, you're going to see a rapid increase in the entropy that exists, or even sublimation, right? Same thing. Sublimation gives you the exact same increase. If you go from a liquid and solid, go from a solid directly to a liquid, you're going to see an increase in the entropy. Maybe not as big as going from a solid to a gas, but still an increase in entropy. So if you have a chemical reaction that occurs, and if you increase the number of gas molecules, right? If you increase the number of gas molecules, your entropy in the system is going to increase. Right? Because it's like to say we have a decomposition, right? We take carbonic acid, right? And it decomposes to give us carbon dioxide and water, right? We're going to see this increase that occurs. Oops. That's really strange. Yeah, Freddie, your microphone got unmuted. I'm muting you. All right. All right, so if you think about this from a chemical reaction perspective, carbonic acid is going to go from one molecule to two molecules, right? You have this increase in the number of gas molecules that occur. You're going to see this increase in the entropy of the system. So here's a picture of some of this going on, right? If we have ice on the left, all the way to the left, right? It's going to be rigid. It's got a crystalline structure. Motion is restricted to vibration only. You have the smallest number of microstates for ice, right? Then you move over to the liquid state, right? In the liquid state, you have increased freedom with respect to translation, right? The molecules can now move around, right? This one, water molecule here can work its way through and eventually end up on the other side of the flask, right? It still has all the vibrational motions that are available to the solid, but now they can rotate freely, right? And then you think about water vapor, the last one, right? Now, since everything's spread out, there's a lot more freedom, right? This molecule has a lot more space. It can travel in straight lines a lot more easily, move longer distances. You have, much easier translation. All the vibrational modes are still available, and rotation is much easier as well because there's no molecules bumping into it, right? So these types of things are able to, you can see how, you can increase entropy just simply going from different states, right? If you think about entropy of a system, we take down below here, you have this solid, right? You have a solid sodium chloride sitting on the bottom of a container of water. And as that solid dissolves, right, the solid is very organized. The solid sodium chloride is very organized, very low entropy. As it dissolves, you have the individual chloride and sodium ions that show up in solution, but they're pulled apart and separated, right? You see you're increasing the overall entropy. So dissolving is an increase in entropy of the process. Let's see here. All right, then you also have, in this particular example, right, where we're taking nitrogen oxide, right, and we're reacting with oxygen. We're going from 3 gas molecules to 2 gas molecules. So this is a decrease in entropy, right? We're decreasing the number of molecules, so we're going to decrease the entropy, right? We're going to decrease in entropy as we go from the left-hand side to the right-hand side. So you can see, and in order for this reaction to occur, there's going to have to be some other effect in the chemical reaction that's favorable, right? And it would have to be enthalpic, so that some enthalpy have to be a favored process here. Let's see. All right, let's go through a sample problem here. So we have, we're going to predict the sign of the change in entropy. So predict whether the delta S is positive or negative for each process, assuming each occurs at a constant pressure. So, just a brief explanation. We expect the change in S entropy to be positive if there's an increase in temperature, an increase in volume, or increase in the number of gas particles. The question states that the temperature is constant, so we need to only concern ourselves with volume and the number of particles, right? So we were told it's constant temperature. So when you're thinking about problems, make sure you're aware of what's going on here, right? This is a constant temperature-based system. We look at water, right? Water going from a liquid to a gas, right? We're changing physical states. Obviously, this evaporation involves a large increase in volume as the liquid changes to gas. Right, 1 mole of water, which is 18 grams, right? Because molar mass of water is 18 grams per mole, occupies about 18 milliliters as a liquid. if it could exist as a gas at standard temperature and pressure, it would occupy 22.4 liters, right? 18, think about that, 18 milliliters versus 22.4 liters, right? You're talking about a graduated cylinder versus, filling up, that's 22.4 liters, filling up, the inside of a car. Maybe that's not quite 22.4 liters. The front seat of a car, maybe. Something along those lines, right? So we're talking about massive change in volume, right? From a graduated cylinder's worth of space up to, enough space that you're, larger than your body. Because the molecules are distributed throughout a much larger volume in the gaseous state, an increase in motional freedom accompanies vaporization. And so delta S is going to be positive, right? Delta S, we're having a positive change. We're increasing entropy. Make sense? Let's see. Turned off the conversation. All right, so then we have, what's going on here? Silver chloride being formed. Silver ions as an aqueous state reacting with chloride ions in the aqueous state, and they precipitate out silver chloride. Right. So in this process, these ions, right, they're aqueous ions, they're free to move throughout the volume of the solution, and then they form a solid in which they are confined to a smaller volume and restricted to the more highly constrained positions, right? So, the solid precipitates out, sits down on the bottom of the flask. The ions are no longer moving around freely. They can't move around the flask. So the change in entropy is going to be negative, right? We're decreasing entropy, decreasing the randomness. We increase the organization by becoming a solid. We have the next example, 4 iron atoms as a solid react with 3 oxygen atoms as a gas to form 2 iron oxides as a solid. Think about what's going on here, right? In this example, we have a solid reacting with a gas to form a solid, right? So we're greatly reducing the amount of movement, right? There's lots of movement that occurs here. And we're going obviously from, 7 different molecules and or atoms to 2, right? Tremendous decrease in the amount of entropy, right? The particles of the solid are confined to specific locations and have fewer ways to move, or fewer microstates than do molecules of the gas, because the oxygen gas is converted into part of the solid product in the iron oxide, so the delta S is going to be negative here again. And look at D, right? We have nitrogen as a gas reacting with oxygen as a gas to give us 2 nitrogen oxides as a gas. That's interesting, right? We have 1 gas molecule plus a second gas molecule gives us 2 new gas molecules. What's going to happen here? Right, so the number of moles of reactant gases is the same as the number of moles of product gases. So the entropy change is expected to be small. Right, the sign of delta S is impossible to predict based on our discussions thus far, but we can predict that delta S is going to be close to 0. So right now, if we were simply look at this problem, based on what we know so far, we expect a very small change because our gas molecule stays the same. All right. We'll talk about other reasons why it's not exactly 0 as we move on through the class. Let's do a sample problem here. Let's go through a sample problem. You do that. Let's see. There we go. All right. So here are 4 different problems, and it's asking you to just determine whether each process produces an increase or a decrease in the entropy of the system. So everyone work through, go A, B, C, D, and give me your answers. Say the A, increase or decrease, B, increase, decrease, and post some in the chat, and we'll go through them quickly. These should be hopefully pretty quick. So take the time. And you can even say, abbreviate, say I or D. Give everybody a couple more minutes, a couple more seconds. Hopefully this is straightforward. Hopefully the first one makes some sense, right? We go from a solid to a gas, so we're going to have the increase, right? The next one, where we're going from a solid and a gas to a solid, we're going to see a decrease, right? Because we're going from gas to solids, we're moving there. And we have gas going to solid, so we're going to have, reduction of movement, so we're going to have a decrease there. And then the last one where we have gas going to gas. So we have to take a look and say, okay, how many molecules are there, right? So we're going to have a 2 reacting with 1 going to 2. So we're going to decrease the number of molecules. So this is also going to be a decrease as well, right? Hopefully that makes sense to everyone. Questions? All right. So let's go back to the presentation. If you have any questions, just pop it in the box there. All right. Let's go through another sample problem. It's predicting the relative entropies. So in each pair, choose the system that has the greater entropy and explain your choice. So take a look at the first one. We have 1 mole of sodium chloride as a solid, or 1 mole of hydrochloric acid as a gas at 25 degrees Celsius, right? So obviously we have a gas. So, oops, pen stop. Okay, there we go. So we have hydrochloric acid is a gas. So it has the higher entropy because the particles in the gases are going to be moving. They're more disordered. They're more freedom of motion than the particles in the solid. So you'd expect, especially because of the fact that we both, this is something we have to start paying attention to. We have 1 mole of each. So the number of molecules, right? The number of moles is equal, in this case, to the number of molecules that are present. Both have 6.02 times 10 to the 23rd molecules floating around. Since they're exactly the same, you would expect the only difference to be based on, again, on their state, solid versus a gas. The next example, 2 moles of HCl as a gas, or 1 mole of HCl as a gas. Again, now we have both exactly the same number of molecules. The difference here is the 2 versus 1. All right, so when the 2 systems are at the same pressure, the sample containing 2 moles of HCl has twice the number of molecules as a sample containing 1 mole. Thus, the 2-mole sample has twice the number of microstates and twice the entropy. So twice the number of molecules, twice the entropy that exists, right? A lot more positions available. C, 1 mole of HCl as a gas or 1 mole of argon as a gas. This is interesting, right? We both are a gas. What's the difference between the two? We both have 1 mole. One is HCl. The other one is just straight up argon. Everyone see there's a bond here, right? This one has a bond. Argon does not. So the HCl is going to have a higher entropy because the number of ways in which HCl molecule can store energy is greater than the number of ways in which the argon atom can store energy. Right? The HCl molecules that can rotate, right? It can vibrate, whereas an individual atom is not going to be able to rotate or vibrate, right? You know, you look at an atom, it's a sphere. Rotation of an atom isn't doing anything in terms of entropy, right? There's no vibration that occurs because it's not connected to anything else. All right. So let's do, there's another sample problem for this as well. Here it is. You have a question. It says, which system has the greatest entropy? And it gives you A, B, C, or D. So figure out which has the greatest entropy. All right, so let's take a quick look at this, right? We have all of them are exactly at 1 mole, right? So the number of particles is the same for each of these. So we can rule that out of the system. Then we have H2 as a gas, H2 as a gas, H2O as a solid, and H2O as a liquid, right? So we can see very quickly, even though H2O is larger than hydrogen, right, than H2, it's a solid, so it's going to have reduced number of microstates. So is a liquid. So both C and D we can rule out because we have solids and liquids versus gases. Then we have to think here, okay, so what's the difference? Standard temperature and pressure, STP. Right, standard temperature is going to be room temperature, right, 25 degrees Celsius. The standard pressure is 1 atmosphere, right? you can see temperatures, very large increase in the amount of temperature that exists here. So we'd expect the answer to be B. Right? So here's the temperature is going to have the biggest effect on the number of microstates. Questions, please pop it in the box there. Alrighty. All right. Third law of thermodynamics. So the entropy of a pure crystalline substance at absolute zero is zero, right? Think about that. At absolute zero, there are no movements, right? There's, we're talking about this point right here. Oops. Again. Right. At this point right here, right? There's entropy is zero, right? There's zero movements, there are zero vibrations, there's zero translations, there's no stretching, no rotations, nothing going on. So they're all atoms, molecules, the perfect lattice at 0 Kelvin. There will be only one microstate. So at absolute zero, there's one microstate. So if W is equal to 1, right, the microstates are equal to 1. Then we can see that our entropy here is going to, after we take, plug in the number of microstates, W in as 1, our entropy is going to go to 0, right? If we only have one microstate, our entropy is 0, right? So we have no randomness, everything goes down to 0. Oh, I see Sophie had a question, sorry. Would the pressure decrease affect the increase of volume? And then we're talking about the last problem. So on that last problem, so the pressure decrease of 0.5 atmospheres is, if anything, you have in order to have 0.5 atmospheres, you're going to have, right, you have a decrease in pressure. In order to decrease pressure, you need to decrease the contacts with the surface, so you probably have to have a larger volume. But it's, does that make sense? Because if you were to shrink the volume, you increase the pressure. So if you're decreasing the volume, right, at 0.5 atmosphere. So yes, so that makes sense. So yes, that is a direct correlation there as well. Sorry, I missed the question before. All right. So if we go back to this graph here, you can see, right, at absolute zero, our entropy will increase, right? Entropy goes up as we start increasing temperature. As we start increasing temperature, eventually we go from the solid state, right, to the liquid state. And during that melting process, we see a direct increase in entropy with no temperature change, right? As we, at the beginning we're completely solid, and by the end we're completely liquid, and there's no temperature change that occurs during the melting process, right? The same thing for boiling, right? We're going from a liquid to a gas, right? During this temperature, there's no temperature change, but we see a rapid increase in the entropy of the molecules, right? The gas molecules are, let's say if it's water, 100 degrees Celsius, the liquid is 100 degrees Celsius. But our entropy rapidly increases because we're going from the liquid state to the gas state. So standard entropies. So the reference point for entropy is 0 Kelvin. So the values for elements are not 0 joules per mole, per Kelvin at 298 K. Right? All this we're saying when we're talking about our pure elements, do not have entropy values of 0 at standard temperatures and pressures. Right? Because our standard temperature is 298 Kelvin. So we obviously can't have, since to have 0 entropy, we have to be at 0 Kelvin. Right? This is the first thing when we're thinking about standard entropies. So standard molecular entropy for gases are generally greater than liquids and solids. And just take note of the size of the gas molecule is going to be very important. The standard entropies increase with molar mass, right? The larger the molecule, the more number of microstates that exist, right? That makes sense. It obviously makes sense here in the previous one. I didn't say so, but right, a gas has more entropy than a liquid or solid. And then standard entropies increase with the number of atoms in a formula, right? More microstates. Again, the more bonds that exist in between each of the individual atoms, the more microstates that exist, right? Molar mass is the same, similar, right? If you have, the larger atoms are going to have more possible microstates, more, we're talking about the larger mass. All right, let's take a look at a table of some of this, right? So in the beginning, from the top portion of the table, everything's in the gas state. So you can see if we move from hydrogen as a gas, we have 130 joules per mole per Kelvin for entropy. Nitrogen, right, a larger molecule, we go up to 191. Then we increase the atomic mass going from nitrogen to oxygen, right? We're increasing, going from a molar mass of 14 or 28 for N2 up to 32 for oxygen. So just simply, right, it looks similar, right? We have nitrogen gas going to oxygen gas, right? We see an increase that occurs. All we did was increase the number of the molar mass. We went up, the number of atoms stays the same, but the molar mass increased. You go to water as a gas. It's interesting, the water as a gas, it decreases a little bit. So we have a slight decrease that occurs when we go to water as a gas. Then we increase it when we move back to ammonia, right? So, and then we increase even further and we move up to methanol, and then move up to C6H6, which is going to be benzene. We keep increasing. You can see as you get larger and larger, there are obviously points right here in between these two where, it's a mixture, right? We have water, right, where we have now 2 bonds in between, because we have 3 different atoms, but we have smaller, right? We have hydrogen atoms. Hydrogen atoms are small, right? Our molar mass here of oxygen is, we're talking a molar mass of 32 versus a molar mass of 18 for water. Okay, so the number, it's not exactly clear what what this breaking point is and what the trend is, but is obviously molar mass, so a decrease in molar mass. So we saw a decrease in the entropy that occurs, even though we saw an increase in the number of bonds. But if we see a direct increase in the number of bonds going from water to ammonia, we see an increase in entropy, right? And then if we compare the last two, we have water as a liquid, compare it to water as a gas, and you can see there's a huge difference, right? 69 versus 188. So a large difference in entropy of a gas versus a liquid. The same thing for methanol, right? The methanol difference is right here. CH3OH, right? Big difference in entropy in the gas state versus the liquid state. All right, there are some additional liquids here, right? So if we compare, oops, there's the gas state of C6H6 at 269 to its liquid state at 172, right? And then we look at solids, right? Here we have solids, lithium being the smallest solid here at 29, then sodium is a solid, slightly larger, 51, potassium slightly larger, 64, iron, you know, it's actually larger, but I mean, it's a larger molar mass, but it's a smaller atom. It's the 27, right? Thinking of solids here. So we have, if you think of the size chart on the periodic table, the atoms towards the left are larger atoms, right? So iron's a smaller atom than potassium, so it has a smaller entropy, diameter-wise, that is. So iron chloride, you can see as a solid. Now we have, 3 bonds between the iron and the chlorides. So we're increased entropy significantly. Sodium chloride, only 1 bond, so smaller entropy. All right. Okay, entropy changes. So entropy changes for a reaction can be calculated in a manner analogous to that by which delta H is calculated. Right, so if you remember back when we talked about the enthalpy, delta H, of our reactions, we had our delta H was equal to the summation of all of the enthalpies of our products minus all of the enthalpies of all of our reactants. Well, the same thing exists here when we look at entropy, right? Entropy, we just plug in the entropy of all of our products minus the entropy of all of our reactants, and we're able to calculate the overall entropy change of a reaction. And again, remember N and M, these are just the coefficients in the balanced chemical equation. Right? So it's just a summation of all of our molecules that are in the reaction. So let's go through a sample problem like this, right? It says calculate the change in standard entropy of the system, or delta S, for the synthesis of ammonia from nitrogen and hydrogen gas at 298 K. Right, so we're just simply reacting nitrogen gas, hydrogen gas, and getting out ammonia here. So we're going to make this calculation using the equation 19.8, which is on the previous slide, and the standard molar entropy values in table 19.1 in appendix C. So all we're doing is plugging it in, right? We have our equation using equation 19.8. We see that our entropy, change in entropy, is equal to twice, right? The 2 is coming from here, twice the entropy of our ammonia minus, so this is products, minus the entropy of our reactants, which is the 1 nitrogen atom and the 3 hydrogen atoms. You can see the 1 and the 3. And we just simply plug, now we're looking from here, we're going to get our entropy values from the table and plug them in, right? 2 times the 192.5 minus the 1 times the 191.5. That's just the numbers right here, right? We have our, oops, I covered it over. We have our 2 times the 192, which is right here, right? Our product, minus the 1 times the 191 for our nitrogen, minus the plus the 3 times the 130, which is coming out of the table here. And we just do the math, we end up with a change in entropy of minus 198.3 joules per Kelvin. So this makes sense. Our entropy is going to decrease. If we think back to the equation, what happens? Right, qualitatively, we have 1 molecule plus 3 molecules, total of 4 gas molecules on the left, going to 2 gas molecules on the right. So you expect entropy to decrease, right? We're going from 4 gas molecules to 2, and it actually is. So we're having a decrease in the number of molecules of the gas during the reaction. All right. So we have time left. A couple minutes. I'll take a couple minutes. We're kind of behind. So, all right. Entropy changes in surroundings. So heat flow that flows into or out of the system changes the entropy of the surroundings. So for an isothermal process, right, the heat of the surroundings is equal to the heat of the surroundings over the temperature, or minus the heat of the system, right? If you think about, we have our system and our surroundings, right? If we have the system giving off heat, then the surroundings are going to increase or have a negative effect of, these based on the system. So at a constant pressure, the heat of the system is simply the delta H for the system, right? So when we're talking about the heat of the system is simply the delta H of the system. And I'll come back and explain this in the next class in more details, but think about, right, because our delta S, right, if we go, is equal to the reverse. And remember the Q reverse, and the Q reverse is equal to what we're talking about here. So you can go back and take a look at those previous slides, and we'll come back and describe this slide in more detail in the next class. All right, any questions before the end of class? Otherwise, we'll have a review tonight, 7 o'clock, cover the exam. If you have any other questions before then, please let me know. I'll work through posting the answer key. Thanks, everybody.